Okay, we start up again. So we had the Gauss-Seidel solution, slow, very slow. So we will try to speed it up a little bit using the omega. So omega 1, that was for Gauss-Seidel. Now I want to have an omega, and for this problem, luckily I found the optimum omega, and the formula goes something like this: 2 divided by, and then we had 1 plus, now what's happening? Go away. 1 plus sine of the number of unknowns, no, p divided by the number of unknowns. So finding these optimum omegas can be very hard, but just for this very simple problem, linear equation, same number of cells in both directions, fairly well possible to find it. Not for you guys, it's beyond this course. For more complex cases, if you are really going to do some heavy simulations, I can recommend something like this. You can take 2 minus and then a number depending on your spacing. Some say 5 of these or 6 of these. So the smaller h is, the closer you get into 2. So play around with these numbers and see if you can find a decent omega. That's one brutal way for engineers. For numerics, they love to find these formulas, and for this one, yes, we can use it quite perfectly. So now I try to go down to 100 iterations. Now the final question is 0.5. That was my scaling. I would like that one to be the maximum velocity for the solution, which I don't have. But we actually have it here. So there you have the analytical solution for our problem. Very easy, very neat. So we only need to program it, and then from this one, just insert 0, 0, we can find the maximum velocity. So I'll use that one. So let's try that one. Let's see, now we have an axis here. Let's see if I recall correctly, I had my program here. So this one actually calculates this analytical solution given the input positions x and y. So we can use this one as a function, finding our proper scale. We can test it down here as well. U analyte number 2, I called it, of 0, 0. Okay, so around 0.3 should be our scale. But let's do it in the program. It's more neat. So instead of 0.5, I want to have U analyte of 0, 0. And I do the same down here. Then we're good to go. No. What was wrong now? He didn't like that. Okay, then we do it differently. I guess you can't have a function call inside an axis. So let us do it like this. 1. And then when we do the plotting, we plot U divided by, just using that one now as a scale. That should work. No, he didn't like that one either. Ah, of course. Analyt number 2 was the name. Where was it? Up here? Analyt number 2. There we go. Not so easy to see actually when you look it in 3D. You see the residual, very, very small indeed. If you want to have it have a view from the side, you could use this one, view 0, 0. Then you see it from the side. Actually better. For a given problem, how many iterations do you need? Well, as a rule of the thumb, I would say in 1 or 2D dimension, really doesn't matter. If you have here 31 unknowns, you have to at least give him the possibility to sort of sweep the information in one direction and back again. So at least double this number here. In 1D it would be the same. If I had 31 unknowns, I should have 60 iterations at least. So this number definitely 2 times the number of the unknowns in one direction. 100, okay, then I have 3 times. That's okay. So if we try, say 101 unknown, then I should have at least, let's take 300 there, just to see how it works. Yeah, even 200 would be quite okay, although the residual is still climbing down. So it's not so accurate as the first one, but decent. And now I have scaled it against the analytical solution, so the center should just kiss the value 1 here in, and actually I think he does it quite nicely. You can test it if you flip it like that, use the plus, and then find the maximum one. It's as good as 1 as I have ever seen, so no problem there. Another way, you could have monitored max of u. Then you will get the biggest one, which then is fairly close to the analytical solution, 0.3. Any questions to that one? That's okay. Now I would just want to compare this one. Let's go back to the 31 and say 100. Compare that one with MATLAB's backslash. Then I cheat. So a little bit magic here. Here we have it. So after finding my solution, I start here by creating, now this one is going to be a pentadiagonal coefficient matrix, since it's in 2D. So you have the same headache in your exercise. Construct this A matrix for a 2-dimensional case. How the heck should you do it? Well, the logic I've used here is sort of straightforward one. You start by setting a counter equal to 0, and then you go through your entire domain, the innermost loop for I, and then the outer for j, and then you just add this counter. And if you are on the center, well, the center coefficient should always then be -4 on the diagonal. And then if you are close to a boundary, okay, then you have to do something special. If not, then you have both active neighbors close to you in both the x direction but then also in the y direction, although there you have to add the number of unknown in one direction, in one dimension, to keep this one correctly. Having found the A matrix and also the right hand side here, just minus h squared for all elements, very easy. You find the solution straightforward, but now remember the solution you have found, that is a one-dimensional vector. Now you have to translate it back into your 2D case again. So here the same counter, and then you have to update the velocities based on this one-dimensional solution. So here I now just plot the exact numerical solution that the backslash provides me, minus the one that I have found, and then I scale it with the center velocity from the analytical solution. So just to have an idea how well I found the solution. Here I then have the analytical solution. That was the big expression that I showed you. And then I compare with that one as well, and make another figure where I take the difference. Now it's the correct analytical solution minus my numerical solution, and the same scaling. Now let's see how these figures compare. Running this one, finding the solution within 100 iterations, and then he crashed. What did I miss now? Yeah, big X. I called it Y here. Surf Y, and also down here. Let's try again. Finding our solution. Still doesn't like it. What's wrong now? Oh yeah? What's wrong now? That was strange. That doesn't really compare. Okay, that one doesn't look too good. I've used the Y already here somewhere. Okay, rename. Now then, try again. Missed one. There we have them. Let's take this one first. That is the difference between MATLAB's backslash and my numerical solution. 10 to the power of minus 6 for the scale, so very, very close to 0 indeed, which sort of mimics my final residual 10 to the power of minus 5, so I have found the numerical solution fairly close. Now the final figure, there I have an adduct which is much bigger. But here, remember, I compare with the analytical solution. So then you can never dream of achieving this one correctly, numerically. It's not possible. Well, in the limit, if you let delta x and delta y go towards 0, this one should be smaller and smaller. But here it really doesn't help if I say increase the number of iterations, 300. Well, we can even take 500. We have time for that. Shouldn't take too long time. Just so that you see the residual should go all the way down to the machine accuracy. And yeah, we could have stopped already. And now if we compare, you see this one is now very, very close to 0, 10 to the power minus 50. This is just numerical white noise. So yes, we have the perfect numerical solution, but why waste the effort? This anode, compared to the analytical, is just as big. So we could have stopped actually when we have an anode of this order, and this is then of course of the order h square. So it's really not, doesn't really pay off. So let's try, well, 50 might be a little bit too crude, but let's see. Nah. You see now the difference between the exact numerical and my solution. It's fairly big, but compared to the correct analytical solution, it's of roughly the same order. So it will actually be enough with say 50 or a little bit more maybe iterations. Okay, you can play around with this this one yourself. Any questions to this square duct? That's okay. Then we try something else. I don't want to use Gauss-Seidel. I don't want to use SOR. I have this direct solver that we used on a 1D case, the TEP4280, the Thomas algorithm. I want to use that one on a 2D case. How can we do that? So using TEP4280 here. Well, yes, it's possible, but how should you then think? Let's say I choose one arbitrary line in the J position here. There I have one J line. And then I sort of treat the following. These unknowns that I have inside my domain, okay, they are the unknown along one single line. Everything else is given. Everything else is known. Meaning, for this recipe, using all the 4 neighbors, I only use 2 of them, and I treat the one at the top and the one at the bottom, the neighbors up and down for this line, as known. So then I just throw them on the other side of the equation sign. That's a dirty trick, isn't it? So for a J line, how should the equation system now read? Well, well, you have your unknowns. What are your unknowns? Well, for an arbitrary line J, my unknowns will be from I equals 2 all the way up to n plus 1. So it will be U number 2, J, U3, J, all the way up to UN plus 1, J. These are my unknowns. Should be multiplied with, and here comes the coefficient matrix. How will that one look? Well, for the diagonal, the main diagonal, we still have the value minus 4. So nothing has changed there. Minus 4 all the way down here. And then for the neighbors in the x direction, well, that's the same. 1 and 1 all the way down. No problem there. So yes, you have the standard 3 diagonal coefficient matrix. Not a problem there. But what's happening on the other side here? Well, we had minus h squared. Now I have something else. What else do I have? Well, for the first one, I'm then going to need these two guys. They are now going to be treated as knowns. Throw them on the other side. So here I will now have minus. Here it was plus, so on the other side it will be minus. And then I need u number 2, j plus 1, and then number 2, j minus 1. And so on all the way for all of them. So you sort of have to design a new right-hand side in the equation system for every step. And then you, of course, you can solve along one single line. That means you have only updated the values here and just forget about the rest. Of course, that's not correct. But then you take the next line and the next line and the next line. You do it for all the lines. And then hopefully the entire field should then have obtained a better value. So this should now be our recipe. Let us try that one. Then we can actually store it, can't we? Let's see. I used the same setup, but I now call it ADI. ADI stands for alternating directions implicit. Coming back to that. But for now, I just, yeah, well, we can keep, no, I skip this one. Delete the comparisons. Now here everything should be the same, but we can now create our, well, we don't need this omega anymore, like that. Then we have to create our diagonals, stuff like that, for the 3 diagonal equation systems. So A was ones, and I then had n unknowns. And C, that was the same as A. That was the 2 diagonals next to the main diagonal. And then we had B, that was the same as A multiplied with minus 2. So there we have A, B, and C. That's all that's required for constructing the 3 diagonal matrix, the big A. So that's actually all we need, because the right-hand side we have to construct for every line, you might say. So we can still keep this residual, but now I only have a one-dimensional line here, like this, for all j's equal to. So now, well, actually we don't need this residual. Can remove him as well. So here for a given line j, what should we do? Well, we have to construct the right-hand side of the equation system. And what will he be? Well, we can construct sort of the start of it at least. That should then be the same as A multiplied with minus h square, like that. And then down here I can say d equals d0. That should be more easy. But then I need to subtract the two velocities. That is not a part of the equation system. And that one was now, what was it? It was u, and then for all the i's, and j plus 1 and j minus 1. So u for all the i's. How can we do that? Well, that's from 2 to n plus 1, comma, and then it was j plus 1. So now I program it on the vector form, taking all in one sentence, and here all the different i's, but now j minus 1. There we have the right hand side. And then we are ready to solve the three-diagonal problem, finding a velocity field, and just call it v, equals TDMR of A, B, C, D. There we have it. But then we have to update the velocity. So how can we do that one? Well, the u for all these i's, 2 n plus 1 comma j, that is exactly what we hopefully has found. There we have it. You have been given A, B and C up here, and this one now construct the right hand side along one single line. You subtract the two neighbor velocities, that is then not part of the triagonal system, and then just solve it. I have one arrow here, I see. So one arrow here. That one is not minus 2 anymore. He should be minus 4. Clearly. Then we have one sweep here for the entire domain, and we plot him, and then we see what happens. So any questions to this one? Let's try it. No, something was wrong. Yeah, res. I don't have any res here. Remove him. And yes, it seems to be working, but 50 iterations clearly wasn't good enough. So let's go to 100. He should kiss 1 when he has found the solution. No, 100 was not good enough. 200, come on. Ah, he's getting there. But you see, this method actually not as fast as the SOR. Now I have taken it in say the X direction. This method is quite good, and when you want to sort of spread the information fast in one direction. I mean, he solves this line in one single operation. But if you have a complex problem, information is propagating sort of in different directions, then you should not only take these lines, but you should take the other lines as well. So now doing the same, but in the X direction. So what will that one read? Well, it will sort of be the same recipe. Here it will then read I, comma 2, and so on. And also here you have to switch. but that should be reasonably easy. So let's try that one. So I just copy this one and repeat it and change the i's, the j's for I, and also here. This one should now read I plus 1. Oops, not there. And then from 2 to n, like that. And also this one, I minus 1. And then all the j's. Just the right hand side has changed. Same solution, and then we update the line number I with the solution that we has just found. Let's try the x direction alone. So I just comment out the old one like that. So let's try this one. Now what happened? It doesn't work. It worked a little bit, but then nothing more. Now that error is not easy to see, I can promise you. And the reason is the MATLAB's way of looking at a vector. This D0 vector, or the D vector you might say, he goes vertically, but this one goes horizontally. And they don't really talk to each other. So here you can see the hint out here. The D that is a full matrix, 31 by 31, he should be a vector. So keep this list open. So there you can sort of find the answer to why the program doesn't work. And you don't get that error. So what should we do here? Well, you just transpose these two vectors like that, and then he should run. And that's not easy to find errors of that type, I can promise you. So now the x works as well as the y direction, and then we remove the comments, and then we should have this alternating directions using both in x and y direction. So that one is quite robust for a lot of problems, and you see now with 200 iterations, yes, we find a fairly decent correct solution, and the center value now should be close to 0.3. Let's check that one. Sorry, close to 1, of course. We have rescaled it. Okay, that was using TEDEMA for 2D. Any questions? No? Then we stop here.